Okay, so let's make progress. These are our objectives. Okay, so I wanted you to share something with us, but I didn't get anything like that. Now let's start with the atom. Let's start with the atom, and let me ask, what's an atom? What's an atom? Helen, do you want to share something with us? Yes, Robert, let's go.
Please, is the smallest unit of an element that retain its identity during chemical reaction.
Okay, that retains the chemical properties of that substance or that element. All right, thank you for your contribution. All right, now when you look at the atom, it is neutral. If you look at the structure of the atom, where we have the protons and neutrons at the core or at the center of the atom and electrons outside the nucleus. When we want to talk about the charges of the subatomic particles, we have the protons positively charged, and then we have the electrons negatively charged. Now, for the atom, it is always that the number of protons equals the number of electrons. And so usually the charges would cancel out, and then we have a neutral atom. However, we have these things not stable. If we want to look at their configuration and we want to use the energy levels or the shells, then we have that at least for the first shell, it should satisfy the duplet rule. And so for the first shell, we should have a maximum, we should have 2 electrons for it to be for it to be stable. And then apart from the first shell meeting the duplet rule, the rest should meet the octet rule. And for that matter, there should be 8 electrons. Okay, so if we have a case that for these shells, we don't have 8, then something is going to happen. Either the atom is going to lose electrons, so that it is now going to have the last shell or the valence shell or the outermost shell now having 8 electrons in it for it to be stable, or it is going to gain electrons so that it becomes stable. Now, anytime any of these happens, it is no more an atom, but now becomes an ion. If it gains to be stable, it is an ion. If it loses to be stable, it is an ion. And so we usually want to talk about ion as a charged atom. When an atom becomes charged, it now changes from atom and becomes an ion. All right. So since it can gain to become an ion or lose to become an ion, then it tells us that we can talk about 2 types of ions. And those 2 types, we have cations and anions. The cation is a positively charged atom formed by losing an electron or electrons. All right, so we've said that for the apart from the first shell, all the other shells should satisfy the octet rule. We may have a case where the electrons in the valence shell or in the outermost shell is not up to 4. We may have 1 in it. For example, if we have sodium atom, the sodium atom has just 1 electron. if we have like the potassium atom, it has just one electron in it. So considering that for just one electron and for it to gain 7 to make it stable, that is too much of a work. And it is easy for it to lose than to gain. So those ones that do not have up to 4, they would prefer to lose the electrons. And whenever it loses, it becomes a cation. So when it loses, we assign it a positive charge. However, the number to add to the charge depends on how many electrons that it lost. If it lost just 1 electron, we just put plus there. If it lost 2, or if it lost more than 1, then we'll now indicate the number. So if it lost 2 electrons, we put 2 there. If it lost 3, we put 3 there. Okay, so now if it's not up to 4, we've said that it is going to the atom is going to lose those electrons. And when that happens, then we have the cations. So cations are formed by losing an electron or electrons. The interesting thing is that for some of the groups directly indicate the number of electrons that are lost, or the number of electrons in the valence shell of the atom, or the number of electrons in the element. For example, if we have group 1, then it means that all the elements in group 1 have just 1 electron in their last shell, or in the valence shell. If we have group 2, then it means that there are only 2 electrons there. If we have group 3, there are only 3 there. I will not comment on 4, those that have 4 in the meantime, because they can lose or gain. And so in this case, before 4, they will always lose rather than gaining. And when they lose, they form cation. When they lose, we assign positive to them. So they form ionic bonds by losing their valence electrons. And by now, if I say valence electron, I think we all have a fair idea of what a valence electron is, or an outermost electron. We are talking about the electrons in the last shell. That is, if you do the configuration, the electrons in the last shell is the valence electron, or the outermost electron. The ionic form of some of the group 1 and group 2 metals are like lithium. Lithium atom forms an ion of Li plus, is in group 1, and so we expect just plus. We cannot write 1 plus, we can only write the plus. So like the lithium, sodium, potassium. And those in group 2, we will have like the beryllium, the magnesium. Group 3 will have the aluminium and the rest. So these are some examples of cations, and we have said that cations are formed when they are formed by the loss of electrons. All right. Then what happens if instead of losing, the atom now gains? And so this, at this point also, we are jumping from 4, and then we are taking it from those ones that have valence electrons of 5 and above. So those that have valence electrons of 5 and above, it means that they are going to gain the number of electrons that will add to what they have already to make it 8. And in that case, they form anion. And so we talk of anion as a negatively charged atom formed by the gain of an electron or electrons. And here we are saying that the number of electrons that you are going to gain, or the number of electrons that the atom is going to gain for it to form the ion, depends on the need or the vacancies for it to get to 8. So if it is 5, it means it is going to gain like 3. If it is 6, it will gain 2. If it is 7, like in the halogens, it is going to gain just 1. And this also tells us about the number of bonds that they can ideally form. Okay, so for example, the maximum number of bonds that ideally an oxygen can form is 2. The maximum number that nitrogen can form is 3. We may have a case where they are going to form more than that under certain conditions. For example, if we have like the hydrozonium ion, that is H3O plus, where oxygen is now forming an excess or 1 more. But what we are saying here is that ideally, they are going to form the bonds according to their charges. So we expect sulfur to form 2 bonds. For monoatomic ions, the charge is equivalent to the group number minus 8. And okay, so for example, the group 7 elements have oxidation state of -1 and exist in ionic form as. So we have fluorine forming an ion of F minus, chlorine forming an ion of Cl minus, bromine Br minus, etc. Friends, any questions on these cations and anions? Please, are you with me?
Yes, we are, sir.
All right. Okay, so let's move on to look at radicals. Radicals are ions which contain 2 or more atoms chemically bonded together. We are now talking about group of atoms that have come together, or group or an ion, but in it we have more than an atom that have come together and they are staying together as a charged unit. So when these are going into a bond, they go together in the group, but then they form one. So for example, like the nitrate ion or the trioxonitrate 5 ion. So you'd see that if the trioxonitrate 5 ion forms any bond and you want to dissociate it, you want to break it, we cannot break it, or we cannot break the bond between the nitrogen and the oxygen here in that chemical reaction or in that equation that we are going to write, because this whole thing over here is now treated as one. And you need these radicals, especially when it comes to writing chemical equations and those things. You need them. You need to know a number of them, and that is going to help you a lot. So we have some examples here, like the dioxonitrate 3 ion, the tetraoxochromate 4 ion, etc. So at least get some of these things into memory. There are some of them that are very common. We come across them almost every time, like the nitrates, NO3 minus, like the chromate, like the sulfate, the hydroxide. These things we usually come across them, like the hydrozonium ion and then the phosphate ion. They are common, that at least at our level we mostly come across them. And so let's get them. They always stay together as a charged unit. and so we don't split them. If anything comes to join them, then we will split it at where, or we'll rather split whatever that is coming to join them away, rather than splitting the bond between, or the bond that is existing in the radical. And then we have our last thing for this session, which is valency. And we talk about valency as the combining number or power of an element or ion. The interesting thing is that it is the same as the oxidation number, or the hypothetical charge that we assign to an element or a compound. But in this case, the valency, we only indicate the number. There is no charge attached to it. So, for example, if we have something like Mg2 plus, its valency is just 2. We are not interested in the charge, whether it is positive or negative. Like the chromate is just 2, even though we have the radical as CrO42 minus, its valency is just 2. So that implies that group 1 elements will have a valency of 1, group 2 will have 2, group 3 will have 3, group 7, they are going to have 1. That's if they form the ions. So we are not interested in the sign attached to it. We are only interested in the number. Is that all right?
Yes, sir.
Any questions? Any questions? Yes, Zachariah.
Please, thank you, sir. Please, sir.
Mhm.
So, what is the difference between valency and radicals?
Okay, so friends, who can react to that? The difference between valency and radical. Otherwise, let me ask, what's a radical? Anyone to help us with radical? Yes, George.
I was thinking that he is asking about the difference between valency and oxidation state. But radical, I think radical is an atom, a group of atoms chemically bonded together with as a negative or a positive sign.
Okay, but can bonded together with a charged unit. So, for example, Zachariah, for example, this phosphate ion here, the whole of the group becomes a radical. The whole of the group with the charge on it is a radical. We can't just put some part away, and then it is the whole of the group, and it should be charged for it to become a radical. So if we look at the examples here, all of them are charged species. Okay, so a whole of the group that is charged. So we are treating the whole thing as a radical. However, the valency is looking at the number of the radical, let's say the charge of the radical, or the number on top of the radical, even though we are not interested in the sign attached to it. So if I'm using this nitrate as an example, then the whole group here, the NO3, and then minus, it is -1 or 1 minus. And the 1 minus is the radical, but the valency is just the 1 on top of it. That is the valency. So valency is the combining number of an element or ion, whilst radical, we are talking of a group of atoms staying together as a charged unit. Zachariah, are you okay?
Yes, sir. Thank you, sir.
All right. And that ends this session. We have some self-assessment questions here that you can try your hands on when you are free. Okay, so we will proceed to the next session, which is session 2. All right. Now we needed especially the radical for us to be able to effectively write chemical formulae. And so in this session, we are going to look at writing of chemical formulae, cell and the chemical formulae and chemical equations. And our objectives are to be able to define binary compound, define ternary compound, and then write a formula for ionic compounds. Let me ask, binary compound, what is it? Whatever that you know about it, you can share with us. When we say a binary compound, what do we mean? Yes, Robert, Arthur.
Okay, sir. Please. Binary compounds. They are compound that have only 2 elements in their combination.
Okay, thank you. Let me go to Godwin also. Godwin.
Okay, yes, sir, please. A binary compound is a compound formed from the combination of 2 different atoms.
Okay. Let's look at it. So binary compounds. They are compounds that contain atoms of 2 different elements only. Let's take note of something here. We are interested in 2 different elements. Let me ask. We know carbon dioxide, right? CO2.
Yes.
Is it a binary compound per our definition? Yes, Godwin.
Yes, please. Carbon dioxide is a binary compound.
All right, thank you. So we are looking at 2 different elements. We are not interested in the number of atoms of those 2 different elements present. Our interest is in the different elements that are present. So we have examples like copper 2 oxide, like sodium chloride, hydrogen chloride, carbon dioxide, which is CO2. Even though we have 1 atom of carbon and 2 atoms of oxygen, it is still a binary compound because we have carbon. The different elements there are just carbon and oxygen. Even though there are 2 atoms of oxygen, we are not interested in the number of oxygen atoms present. We are only interested in the fact that those 2 are we only have oxygen and carbon there. So that makes a binary compound. And if it's a ternary, then it means that the compound contains atoms of 3 different elements. So we have some examples there, like iron nitrates. If we look at it, we have iron, we have nitrogen, and then we have oxygen. So we have three different elements there, irrespective of the number of atoms present. We have like the tetraoxosulfate 6 acid H2SO4. We can count oxygen as 1, sulfur as 2, and then hydrogen as 3. We can talk about more examples, but whatever examples we want to mention, we are to ensure that we only have 3 different elements present. So in writing a formula, we are combining elements, or we are combining atoms. And how do we do that? Now, your ability to write a correct formula is very important in chemistry. And we've got some steps here that can help us to write or to write the chemical formula of compounds. The first thing to do is to identify the ions in the compound from the IUPAC name of the compound. Obviously, you'll be given the name of the compound, the IUPAC name of the compound. And so if you know the IUPAC name of the compound, at least it becomes a bit easy to proceed. You need to identify the ions present. And this is the point where the knowledge of radicals is very important, so that you know how to split, or you know how to write the ions present. And then you write down the valencies of the ions. So you've been able to identify the ions that are present, and now you proceed to write their valencies. But mind you, what we are doing now has got to do with ionic compounds. We are writing ionic compounds and inorganic, because how we're going to write a chemical formula for these compounds will be different from how you're going to write for organic compounds. The same methods will not work for organic compounds. If the valency of the cation equals the valency of the anion, then the two ions can combine to form the ionic compound. In other words, it becomes a neutral compound. We'll look at some examples. And if the valency of the cation is not equal to the valency of the anion, then we multiply both ions by a factor so that they will be equal before they combine. We are going to pick an example and we'll use to explain these methods. Then the number of each atom that combines with the other is written as a subscript against them. If the number that's combined is 1, we do not write any number. We only write a number that is more than 1. If it is a radical that is combining with another element, the radical is put in a bracket and its number combining is written as a subscript outside the bracket. So let's take an example. We want to write a formula for sodium oxide. So for sodium oxide, the ions present, we have sodium, and the oxide represents oxygen. So we'll write their ionic forms, or we are writing the ions for them. So sodium ion, sodium is in group 1, and so it will form a cation with a charge of +1. Now, whenever you are writing the ions, make sure that you write the cation first. So we couldn't have written oxygen and then sodium. Always we write the cation first. So the cation here is sodium, that is Na plus, and the anion is oxygen. Now, of course, we should know their charges. If you are confused, if you've written and you don't know the charge, if it's a radical, check your radicals. If it is not a radical, check the group of the element, or check the number of electrons in its valence shell, so that you will know. Godwin, is it a new hand or an old hand? Godwin, is it a new? Okay, thank you. So you check the group, and then you check the number of electrons in its valence shell to see the number of electrons left for it to reach 8. Then that becomes the charge. So as we've written it like this, what we are going, we are not writing an ionic compound. We are not writing a compound that is charged. We are writing a neutral compound. Let's say a neutral ionic compound. So what do we do? What we have here is just like writing one sodium atom and then 2 oxygen atoms. So we want to write something that we will not have any charge. But as it stands now, we have 1 of the sodium, but we have 2. So we have +1 here, but at this side we have -2. So what do we do for the charges to cancel out? What we need to do is that we need to get 1 more of the sodium, since each one will contribute a charge of +1. So if we get 1 more of the sodium, then we are now going to get 2 of the sodium atoms, and each one with a charge of +1. So +1 plus +1 will give us +2. So that at the end, we are going to have +2 here, -2 here for it to cancel. But usually, if you look at it very well, if you cross their charges, it works for all of them. If you cross their charges, it works for all of them. So you cross and then check. If after crossing they are the same, they will cancel out. So you just write it without any subscript. But if you cross and they are not the same, then you are going to write them as subscript. And in one of the procedures, we saw that if you have 1 to be written as a subscript, we don't write it, we just leave it. Okay, so for this that we have here, if we are just crossing it without going through a very long process, then what we're going to do is that we are going to give the 2 here to the sodium, and then, or the 2 here will come and replace the sodium, and then sodium, which has 1, will come and replace the 2. So we need 2 of sodium atoms to balance the oxygen. And so if we do that, we are now writing the 2 of the oxygen as a subscript to the sodium, and the 1 of the sodium as a subscript to the oxygen. But it is 1, and we are not going to write 1. So that becomes our sodium oxide. Friends, is it clear?
Yes, sir.
Okay. All right. So let's move on to look at another one. Okay, so this time around we have copper 2 oxide. Copper 2 oxide. What are the ions present? We have Cu2 plus and O2 minus. Just as we did for the sodium, we're going to do the same for this. We are going to cross them, but when we cross, we know that we are going to have -2 for copper. If we decide to cross them, we're going to get -2 for copper, +2 for oxygen. So -2 plus, what is -2 plus +2? What do we have?
0.
It is 0. So it means that we are only going to write CuO, because As this is positive 2, the other one is negative 2. So they can cancel out straight away. And we have CuO. CuO. But remember that copper is a transition metal and it doesn't have a fixed oxidation state. So I want you to try this. Write the formula for copper 1 oxide. Copper 1 oxide. So instead of II, it's just I. So copper I oxide. I want you to write the formula for copper I oxide and then tell me what you have, what it is going to be. Copper I oxide. Yes, Robert.
Sir, please. I have Cu subscript 2O.
Okay, very good. Oh, that is excellent, Josephine. Thank you. So we're going to get Cu2O. Because if it's copper iodide, it means that the charge of the copper is just plus. So we'll just cross them and we go our way. So thank you very much. Let's move on. Okay, so let's look at the case where we now have a radical in it, and it's still going to be the same. This should be NO3. Let me type in that. That is NO3. All right. So we've got aluminium trioxonitrate 5, and we want to write for it. So at this point, we have a radical there. We should know the ions we are going to write. We have aluminium as the cation, and we write the cation first, or we write the metal first before we write the non-metal. So we have aluminium. Aluminium is in which group does aluminium belong to? Friends, which group?
The group 3.
Thank you. It's in group 3. So it will have a charge of 3 plus. It is going to lose 3 electrons. So a charge of 3 plus. So aluminium and the nitrates. All right. So I think let me put this thing well. Yeah. Yeah. So Al3 plus as against NO3 and then minus. So if we decide to cross them, then what's the 3 that we have for aluminium will come to the nitrates, and then what we have for the nitrate, which is the one, will go to that of the aluminium. So what this means is that for this whole group, we are taking it as 1. So we are going to need 3 of it, because this whole group has a charge of -1, whilst the aluminium has a charge of 3. So we are going to need 3 of this whole group. So we need 1 and another group and another group. So that when we combine their charges, we're going to have 3 of them, as against to come and face that of the aluminium, which is 3 plus. But it still works if we cross them. Now, if we decide to cross, the interesting thing is that since this NO3 is a group, we cannot just, if we decide to, this 3 here, if we decide to come and write it as a subscript here, there's already 3 there. And mind you, this 3 over here does not belong to the group. it belongs to the oxygen. The moment we come and add 3 here, it becomes 33. It becomes NO33. What that means is that there are 33 atoms of oxygen in there, which is totally wrong. Maybe you will burn a chemistry lab. So what do we do? What we have to do is that, okay, let's keep the 3. Let's write the 3 in a way that it will belong to all of them. So for us to write it, we are still going to write it as a subscript, but let's write it in a way that it's going to belong to all of them. So the best way to do that is now to put this whole group in a bracket, and then we'll write it as a subscript. So this thing that we have here, okay, so the aluminum had a charge of 1, so the nitrate had a charge of 1, and so the aluminum is to a subscript 1, but we are not writing it because it's 1. And the 3, we are putting it outside the bracket. The 3 outside bracket here indicates that the 3 here is multiplying the whole of what we have in the bracket. So it is multiplying the 3 such that we have three atoms of nitrogen, and it is multiplying this 3 also, this 3 of the oxygen, and we have 9 here. Someone will say that, okay, if that's the case, then why instead of writing the 3 outside bracket, why don't we share it for them, so that we're going to have n subscript 3, and then maybe O subscript 3 times 3, O subscript 9. Now, mind you, one of the laws of the chemical combinations, the atoms should combine in their simplest whole number ratio. And so if we have N3 and then O9, we can still divide through. We will still divide through, and that will take us back. So let's just put this in a bracket and then write it back. So anytime we have a radical and we have a subscript to write, then if the subscript is not 1, what we have to do is we are going to put a bracket and then write the subscript outside the bracket for them. And if it is outside there, then they are multiplying, or it is multiplying what we have in the bracket. So we have another example here, which is sodium nitrate. Let me give you one for you to write for me. So I want you to write the chemical formula for aluminium sulfate. Ammonium sulfate. Sorry, ammonium sulfate. So let's do it. Let's write for ammonium sulfate. Ammonium sulfate. And then aluminium oxide. So let's do for 2 ammonium sulfate and then aluminium oxide. I think in the next 2 minutes, let's quickly do that. Please, are we doing ammonium sulfate? Okay, we have NH4S. Okay, so the sulfate is SO42 minus. I've had one response. Let me see. We have like NH4SO2. Okay. Yes, Robert.
Sir, please, because of the network, I didn't hear the question.
Ammonium sulfate. Ammonium sulfate. The formula for ammonium sulfate. Okay, we have the aluminum oxide there, Al2O3. That's good, Josephine. Thank you. Left with the okay, Robert. What do we have?
Sir, please, ammonium sulfate. The formula is
Mhm,
bracket open
mhm,
bracket open
mhm,
NH4 bracket close
mhm,
subscript to
mhm.
SO4.
Okay, thank you. Do we all have that? Okay. Yeah. Okay, so let's quickly look at that. Then you compare with what you have. Let me add a new template, a new one here. So we have ammonium sulfate. The ammonium is NH4 plus, and then the sulfate is SO4. SO4 2 minus. We have this one, something like this, and then we've got this and that. Okay, so if we are to cross them, it means that we are going to write the 2 as a subscript to the ammonium, and then we're going to write the 1 as a subscript to the sulfate. This is 4, SO4, we should have 4 here, SO4 2 minus. Good, so something like this. So we need to open a bracket, just as we did for the other ones. The ammonium is a radical, so the whole group has a charge of 1. So this whole thing is a radical. So if we are writing a subscript, then we need it in a bracket. And since it is the metal, we write it, or since it's the cation, since it's the cation, we write it first. We always write cation first before anion. So we have bracket open NH4. Let me just copy and paste it inside it. We have NH4 bracket close, and then we now write the subscript, which is 2, and then we have the SO4. So this is our answer, or this should be, yes, Robert. The charge is not there.
Yes, that's what I wanted to say.
All right. So this should be our how many of us got it correct? Okay. All right, good. Thank you. You all tried. So Charity, you tried. Thank you for the effort. Yeah, you tried. Thank you for the effort. So I think if there is any correction, you can do that. All right, thank you all. Let's move on to the next session if there are no questions. But if there are questions, please ask and let's look at it. Are there any questions? Okay, Robert.
Sir, please, per the definition that we had for the ternary compounds.
Mm-hmm.
I want to ask if carbon dioxide was still fit in that.
No, carbon dioxide cannot fit into a ternary. Remember, the difference is in elements, not the number of atoms. Carbon dioxide, in the carbon dioxide, we only have carbon and oxygen. And I was explaining that we are not interested in the number of atoms, but we are interested in the different atoms present or different elements present. So even though we have C as one atom, and then we have two of the oxygen atoms, it is still the oxygen atoms belong to the same element. So it forms just one element. And the carbon also is one element. So there are two different elements there. And for that reason, or for that matter, it is still a binary compound.
Okay, sir, please, can you please go back to the slide? It's because of the examples, or I don't know if binary compounds are for how do you call it, monoatomic compounds, and the ternary are for polyatomic. Because I saw an example like that. That is why I'm still saying if carbon dioxide could, please, can you go back to the slide?
I'm coming. I closed it totally. So let me look for it and open it. That should be. Give me some time to go back to it. And that was session. Okay, let me see.
I guess it will be in section 2.
Session 2. Yeah.
Yes. All right.
EC1. Okay. Yeah, you said binary.
Yes, binary and ternary.
Yeah. And now, so what is the concern?
Yeah, sir, please, I'm talking about the example like the iron 2 nitrate. You see, we have only one ion over there, and the nitrates are 2. And again, when you look at the ammonium sulfide, the ammonium is 2 over there, and the sulfur is just
Okay.
1. So
Okay, so let's
when I look
look
at
at
the
it.
carbon dioxide,
Okay, so let's look at it this way. In each of those cases, let's try to identify the different elements present or the different atoms present. Can we identify them? Let's start from the iron nitrate. We have iron, that is 1, right?
that's ion.
There is nitrogen, that is 1. There is oxygen, making it 3, right?
Yes.
Do we have any other different atom or elements there?
No, sir.
Okay, so we have 3. That is why I said that we are only interested in the different species present, not the number of them. So we can have thousands of oxygen, we can have thousands of nitrogen, we can have thousands of iron. We are not interested in the number of the same atoms present, but we are interested in the different atoms present. So when we look at this ammonium sulfide also, we've only got nitrogen, hydrogen, and the sulfur.
Oh, okay.
So we are not interested in the number, but we are interested in the different elements or atoms present. Is that all right?
Yes, sir. So that is why I was asking if the binary compounds like occur in only monoatomic like compounds. Like when you look at the carbon dioxide is CO2. So carbon is one, then oxygen is also one. But looking at the iron nitrate, because of the radical, the nitrate group over there, that is why it's rendering it as a ternary compound. That's how I want to understand.
Okay, so and that is why I'm also saying that we are only interested in the different, irrespective of how it is written, the number of atoms that have been written there. We only, if we are counting how many different atoms are there, that is what
Okay.
is going to make it either a binary or a ternary.
I understand it in that sense. Okay, so
All right.
thank you.
All right, you are welcome. Okay, so let's move on to look at the next, which is session 3. Okay, so in this session, we are going to look at the types of chemical formulae. Sometimes you need to write chemical equations, and to be able to successfully complete the equation, especially when it comes to the products, if you are just writing the reactant, maybe sodium hydroxide plus something, or HCl, hydrochloric acid plus maybe calcium carbonate or something, is easy to write. But sometimes completing it, writing the product becomes a challenge. And the what makes it a bit easy is sometimes knowing the type of reaction you are looking at. If you know that, it becomes easy. But in knowing that also, we should also look at the how to write the formula. So in this very session, we are going to look at the 3 types of chemical formulae. And when we are done with that, we'll now look at the types of equations so that we can easily write reactions. So our objectives are to be able to differentiate between the types of chemical formulae, determine empirical formula for an experimental data, and then determine molecular formula from an experimental data. And in fact, as a matter of fact, some of you are going to end up being chemists. I'm sure you are, though you are training to become teachers, some way, somehow, some of you may find your ways in becoming somebody else rather than teacher. And in case you find yourself in a lab, you may be presented with a sample, and you have a sample, you have to at least determine the formula and all those things for something that is very important to be done. And you can just be given a sample, and you need to at least write a formula of whatever compound that is present in there. Okay, so in that case, what do you do? In that case, there are 2 things for you to do. You do your qualitative determination to establish the different elements that are present in the sample. Then you proceed to do the quantitative determination. And so there's always a qualitative test, and then we have the quantitative. So you do the qualitative to know that, okay, this sample, we have carbon in there, we have sulfur in there. So you may be testing for these elements. You will test for carbon, you will test for maybe hydrogen, you will be testing for sulfur, you test for them. So when you have them, then now you need to establish a formula. And so we are going to look at that. Interestingly, we are not going to look at the qualitative determination, but we're going to do the quantitative so that we can write molecular formula. So we have three types of chemical formula. We have the empirical formula, the EF, we have the molecular, and then we have the structural formula. The empirical is the simplest formula of a compound, which expresses the ratio of the number of different atoms present in the molecule or compound, whilst the molecular formula expresses the actual number of each kind of atom present in a compound or a molecule. The structural formula, on the other hand, tells us how the atoms in the molecule are bonded to each other. So we can have a structural formula of a molecular formula. We can have a structural formula or the structure of an empirical formula. So the structural formula is only giving us a fair idea, or is only telling us how the atoms are bonded to each other, and it is very important in chemistry. So we have an example here. We have a compound. Which compound is this? Has any one of you come across it before? Okay, Arthur.
So please, it's ethane. The name is even there. Ethane.
All right. Yeah, but okay. So for this compound, we have the empirical formula CH3, which does not actually help us to know the compound very well unless we proceed to look at the molecular formula. That gives us the actual atoms, the actual number of atoms present. And we have the structural formula. So this structural formula is the formula of this molecular formula as we have here. So we have 2 carbon atoms and then 6 hydrogen atoms over here. So I want you to start with glucose. You'll give me 8 empirical formula and molecular formula. Maybe you cannot type to show the structural formula of the glucose. So just give me the empirical formula and the molecular formula of glucose. Yes, Robert.
Yeah. The empirical formula is going to be CH2O. Then the molecular formula is going to be C subscript 6, H subscript 12, then O subscript 6.
All right, thank you. Friends, do we all agree to that? All right, thank you. So the point is that if we are moving from empirical formula to molecular formula, we multiply by a number. If we are reversing, we divide. We divide so that we get the simplest whole number ratio. so that we get our empirical formula. Okay, so let's look at how you can write empirical formula, and we'll proceed to look at molecular formula. So let's say you are a chemist in the lab, you've done your qualitative and those things, you now know the elements that are present. How do you write your formula? You cannot straight away write the molecular formula. You can start from the empirical formula. So the first thing to do is to write down the different atoms present. So we're going to write all of them down. And when you finish, write the mass or percentage mass of each element or atom under it. Then you divide the masses or percentage masses by their respective atomic masses. You divide through by the smallest value, and then you convert to whole numbers because we write them in the simplest whole number ratio, not decimals. Then now you write the formula of the compound by putting the elements or atoms together with the whole numbers of each as a subscript. Then from there, you can proceed to determine the molecular formula. So once you know the empirical formula, you use the equation into bracket empirical formula times n equals molecular formula. And the n here is the number of empirical formula units in the molecular formula. And after that, you multiply the empirical formula by that number. You cannot just decide to pick a number and use to multiply. For example, in the case of the glucose, where we have the CH2O, the CH2O, you cannot just decide to use any number at all. You need to determine the number that you can use to multiply so that you are going to get the right compound. And we are to note that if we are given the vapor density of the compound, then for us to get the molecular mass, we need to multiply the vapor density by 2 so that we can get the molecular formula. So we have an example here to try. A compound containing carbon. So we assume that the qualitative is done already, and we are being given data for the quantitative. So a compound containing carbon, hydrogen, chlorine, and oxygen as a constituent elements gave the following elementary analysis: carbon 56, hydrogen 3.9, chlorine 27.6. The question is silent on that of oxygen, and it is silent because we are dealing with a percentage, and if it's a percentage, we are talking about 100. So if we have been given and we are left with 1, it means when we add them and then we take it from 100, we will get what is left. And we are to determine or deduce the empirical formula. All right. Since we know the different element present, it makes our case simple, and it makes it simple for us to deal with it. So we have our carbon, we have our hydrogen, we have the chlorine, and we have the oxygen. So per the steps that we went through, the next thing is to write these percentage. Now, the percentages as we have here were masses. They were masses of the elements that have been converted into percentages. So we have the percentage masses written here. Take note, when we are writing a formula, we use their moles. We write them in terms of their moles. And so what we need to do is to find the number of moles of each of the elements. And what's the formula for finding moles? Amount of substance in moles. What's the formula? Anyone to help us with that? Okay, Robert.
Please, is the mass over the molar mass of the substance.
Okay, thank you. George, do you agree with Robert? Okay, thank you, Charity. Thank you very much.
Yes, sir.
Okay, so if we all agree, then it is mass over molar mass. Do we see that formula here? Do we see it here? If you can see my cursor, can you see my cursor?
Yeah, yes, sir.
So can we see that formula here? Mass over molar
Yes,
mass. Can we see
yes,
it here?
yes,
Good.
please.
So that formula is here. So we are only finding the number of moles. These ones, like I told you, are masses that have been converted into percentages. So in some cases, you just use the masses straight away instead of converting it into percentage before you come in. Yes, Charity.
Sir, please, if a question is given, will the percentages be given as in this question, or it is not always usual?
Okay, so either you have the masses or the masses being converted into percentages. If it is not given, you will have enough data to determine the mass of each element that is present.
Okay, sir, thank you.
For example, they could have given us just the mass of the whole compound. And in that case, we could have still found the masses of each element present, even though we would have gone beyond this. We would have done some calculations before getting here. But if not the case, you will have either the masses or the percentage. It could even be in decimals or something. But we have the amount of substance determination here. So we have mass over molar mass. Here is no molar mass because we are only dealing with atoms. So we are doing atomic masses. If it was a whole compound, it would have been molar mass. So mass over the molar mass over here. And that is why we have carbon, which is having a percentage of 56 over the relative atomic mass of carbon, or the atomic mass of carbon, which is 12. So whatever value we have here is the number of moles. And same for hydrogen, same for chlorine and oxygen. Ideally, we have finished with the empirical formula. So we could have just written C subscript 4.67, H subscript 3.9, O subscript 0.78, and then Cl subscript 0.78, O subscript 0.78. But remember, when we're defining empirical formula, we said the simplest whole number ratio. These are not whole numbers. Are they? They are not. If they are not whole numbers, then we have to convert them into the simplest whole numbers. At this point, the chemistry is finished. There with mathematics. Once we have done mass over molar mass, we found the number of moles for each element. What we are left with is mathematics. So anytime you get to this point, remember that you have the masses. The next thing to do is to find the number of moles of each. All right. Now, one way to help us to convert this into whole numbers is to look through and then divide through by the smallest number. And if my sight is correct, the smallest number here should be 0.78. Do you also see the same thing as I'm seeing? Okay. So if you are seeing the same thing, then when we get to this point, we say that we are now going to divide through by the smallest number that we have here, which is 0.78. So everyone divided by 0.78. That gives us the values as we see here. So if we have this, it is very safe to round this one up to 6. 5.99 is almost 6. So we round it up to 6. So we are done with the subscripts that we are going to write. Once we have these things, we can now write the elements, the atoms together. Instead of spacing them like we started with, we will now write them together and write the number under each as a subscript. So C6H5ClO. We are done with the empirical formula. Any case or any question that wants you to proceed to find molecular formula, you'll be given either the molar mass of the compound or you'll be given the vapor density, so that when you get to this point, you can proceed to find the molecular formula. My good friends, any questions? Are we okay?
Yes, sir.
All right. And there is another question here which follows similar. I wanted you to try it, solve it, but I think we are also considering time. So let's quickly go through that. An organic liquid A was found to contain those percentages, and this time around we've been given vapor density. That should tell us something. We have vapor density there. It means we will be going further to find molecular formula. And so we'll follow as we did for the first. We have the percentages written under them. We find the molar, the number of moles, and then we'll divide through the smallest number, and those ones that we have to approximate we'll do. And when after that we have our empirical. I have rushed through that because I took my time in the first question, and up to this point is the same as that. So when we get this, we are now going to find the molecular formula. And if you remember, during the steps, we said that if you are given vapor density, then 2 times the vapor density gives you the molecular mass or the molar mass of the compound. The compound that we are looking for, its molecular formula. So we multiply the 30 by 2 so that we get our molecular mass, the mass of the molecule. That is 60. In some cases, you'll just be given the 60 straight away. You don't have to work this thing out. Then we'll now go for the formula that we were given, empirical mass. So we need a number that we're going to use to multiply this formula to get the molecular formula. But we can't just sit down and say, oh, let's multiply through with maybe 5 or 6. We can't do that. That is not chemical. But this time we are speaking chemical language. So we need to work it. So empirical formula or empirical mass times M is equal to the molecular mass. So the molecular mass is what we have at the top here. So the molecular mass is 60. What is the empirical formula? The empirical formula, we have our empirical formula here, and that is what we are going to multiply. So we have this thing inside this bracket and then times N. We wanted empirical mass. Now the empirical mass, we assume it to be the molar mass of the empirical formula that we have written. That's why we have our empirical formula written here. So we want the mass of this empirical formula, or we want the let's say molar mass of this empirical formula. So we go back to our determination of molar mass. Carbon has atomic mass of 12. So 12 times the number of carbon atoms present. There are 3 carbon atoms. So 12 times 3. Bracket goes. Plus, then we'll move to hydrogen. There are 8 atoms of hydrogen here. The atomic mass of hydrogen is 1. Please, for the atomic masses, they are on the periodic table. They are already determined. So I'm just picking them. You don't need to do calculations to find the atomic masses. They are already there. Oxygen is 16, hydrogen is 1, carbon is 12, calcium is 40. You can look for more. Thank you. So we do for the hydrogen, then we do for the oxygen, which is also 16. The atomic mass of oxygen is 16, and the number of atoms here is 1. So after writing this whole thing, we now work n out. So we have 60n is equal to 60. We divide through by 60, and that gives us 1. That is so interesting. What it means is that the empirical formula is a molecular formula in it. It's an empirical formula, and it's also a molecular formula. That's telling us that it's not all the time that we are going to multiply empirical formula to get a molecular formula. So having gotten 1, then now we go back and then we multiply this whole thing by the n, which is 1. And that gives us C3H8O. So this is our molecular formula. That does not also mean that when we got here, we could have just written this as empirical formula and it's also molecular formula without showing that it is a molecular formula. Because working it out, we could have gotten a different number here. So we can't just, as we've gotten here, we can't just write that the molecular formula is also this. You need to work it out. We have this because we have worked it out, and that is the answer we had. Is that all right? Okay.
Yes, sir.
All right.
Yes, sir.
Okay, thank you. And we end this session here. There is this question over there. At least you can go and try your hands on. So if there are questions, you ask. If there are no questions, we will proceed with the next session. So let me share. That is 4. So in this session, we are going to look at chemical equations, and our objectives are to be able to define a chemical equation, balance a chemical equation, state the types of chemical reactions, and write combination reactions. Now, one advice that I'll give you is that when you are free, try to work more difficult questions. Try to apply the knowledge that you are gaining on different questions to see how well you have grasped it. Okay, so chemical equation. There's a symbolic and quantitative representations of the changes that occur in the process of chemical reactions. We've added reactants, we've put reactants together. They have given us a product. We need to write something to show, to summarize the whole thing, to show whatever that has happened. In chemical equations, we have 2 types. We have the symbolic equations, and then we have word equations. What's a word equation? For example, I can say that in the process of respiration, there is glucose. I can just write word glucose plus oxygen gives, or then I'll put the arrow there. Then I'll write carbon dioxide plus water plus adenosine triphosphate, ATP. I can just write that. That's a word equation. I can also write using symbols so that the glucose, I'll write C6H12O6 plus O2 going into maybe CO2 plus H2O plus ATP. That's the adenosine triphosphate. So those are the two types. But the issue is that one is for babies and one is for adults. The word equation might definitely be for babies and the symbol is for adults, because anytime you write, if I'm just writing glucose, it is very simple until you want to write a formula. Then the issues will pop up. And when you write a word a symbol equation, you need to also balance it. That is also something of much concern. But at your level, we should be looking at a formula, symbols, rather than word. And so for a chemical equation of the form AX plus BY going into CP plus DQ. This equation that we have has two components. One component is the reactant. The other component is a product. A and B are the reactants, while C and D are the products. Now let's take note that in a reaction with a single-headed arrow, the product is always at where the head of the arrow is. The reactants are at where the tail of the arrow is. I will not want you to stick to something that we normally say that always the product is at the right and the reactant is at the left. You may have a case where you have a long cycle of equations such that at a point, instead of an arrow with the head pointing to the right, it's rather the tail that is pointing to the right for the head to point to the left. So if we are still holding that, then we are still going to say that the product is at the right. So what is at the tail is the product. No, the product is at where the head of the arrow is. The reactant is at where the tail is. You may have a double-headed arrow. If it's a double-headed arrow, then what it means is that the reactant is a reactant and can be a product. The reaction may proceed in both ways. So at a point, you have one at one side reacting to give you a product, while the product can also be a reactant coming together to give you the product which was initially a reactant. But if it is of this form, then what is at the head is the product. And X, Y, P, and Q represent the relative numbers of moles of the reactants and products. So the X here, the Y here, the P, and the Q are the relative numbers of moles of reactants and products. And that is where balancing takes place. Anytime we want to balance equation, those are the areas where we'll be manipulating. We cannot manipulate anything at the right side. For example, if it is AX and the X is here, and we want to balance, we cannot touch it. We can only manipulate something that is before the element or the compound. That's in place of X, Y, P, and Q. So like I said, when you write a symbol equation, then let me borrow a term that they use in a law or something. They'll say is it the onus? The onus is on you. You bear the responsibility of balancing it. You cannot just write any equation like that and leave it. You need to balance it. Now, one benefit of balancing equation is it tells you whether you've written the correct equation or not. If it's a bad equation, if it's a potential hazardous equation or equation that can burn your lab, you will try, you'll not be able to balance it. as you try to put 2 somewhere, you need to put 8 at another part. As soon as you go and put the 8 there, another part will be 5. You have to put 5 there. When you finish, by the time you finish putting 5 there, the 2 that you started with now demands that you write 3. You'll be going in a cycle and you will never finish. So if we write equation and we balance it, at least it tells us that we've written a correct equation. So a balanced chemical equation is one which has the same number of atoms of each element on each side of the equation. The underlined word here is same number of atoms, not same combination. Let's take note of that. Same number of atoms. So what it means is that if we have 5 iron atoms here and there are 5 iron atoms here, iron is balanced irrespective of how it is being combined or how it combines with any other element. We are not interested in that. Our interest is if we are counting the number of atoms, we should have equal number of atoms for each atom present. So let's try and see if we can balance this equation. Iron plus oxygen giving us iron oxide. Looking at this equation very well, let's compare the left to right. At the left side there is 1 iron. At the right side we've got 2 iron atoms. Oxygen is 2 at the left, it is 3 at the right. So what do we do so that at the end both sides we're going to have equal number of atoms? But in so doing too, we don't want to use huge numbers. So take note of this. Anytime that you balance an equation and you have to come in with a number, look for the smallest number that you can put there. So if 2 will do, 4 will do, go for 2, don't go for 4. If 3 will do and 6 will do, go for 3, don't go for 6. Okay, so let's see. We have analyzed it. There is 1 atom of iron, 2 of oxygen at the left, there is 2, 3 on the right. So to balance the number of oxygen atoms, we need to write 3 in front of the oxygen gas and 2 in front of the iron. So we have 3 in front here, and then we have 2 here. Now, there is not a formula or a particular formula. Well, in hydrocarbons, there are formulas that you can use to write equations for combustion reactions. But here, there is not a particular formula that you will say that, oh, we use this formula, so that you just apply the formula and it works for you. You need to manipulate. You need to manipulate. But sometimes it is good to start from the complex compound so that maybe a simple compound or even an element that is standing alone, you attend to it at last, since that one you can easily deal with it rather than dealing with a group of atoms or a complex compound. Now we had a simple equation, and so we have to put 3 in front of the oxygen and then 2 in front of the product. Let's see. When we do that, we now have 6 oxygen. 3 times 2 is 6. 2 times 3 is 6. But the iron, we only have 1 at the left, 2 at the right. So obviously, we'll put 2 in front of the iron here. If you look at it carefully, we started the balancing now between the Fe and the O2. The O2 was more complex than the Fe. We have 2 atoms here. We had just 1 here. It was safe and it was good to start from the oxygen here. Or at the right side, if we had more, then we'll look at which one that is a bit more complex and we'll start from there. That makes it's not a formula or so, but it makes it easy for us when we are trying to balance. But in all, we do manipulation, you need to manipulate. If it is if you are doing something right, it becomes a bit easy for you to balance, especially if you have written a correct equation. Other than that, it becomes hard to do so. You can try your hands on more equations. Try balancing more equations. Practice. If you practice more, it's going to help you out. And let's say at the lower levels, there are some equations that you will come across them a lot. So at least if you know those equations, how they are balanced, when you come across them, you write them. But it's also good to know how the balancing is done, of which there is not a particular formula to use, but you would have to be manipulating them. When you are free, try your hands on more complex equations. Our next thing to do is to look at the types of chemical reactions. You need to write a word equation, you need to write a symbol equation, you need to balance it. But knowing the type of reaction helps you to write the equation so that you can balance it. And with the types, we have the direct union or combination reactions, we have the decomposition reactions, we have the displacement, we have the metathesis or the double displacement reactions, and then we have the combustion reactions. So let's go with the combination. The combination is just like A plus B giving us AB. It's very simple. So with the combination, we have two or more substances combining, but they are going to form a single product. They are going to form a single product. Even if there are 5 or 6 compounds coming together, we are going to form a single product. So it can be A plus B giving us AB, or A plus B plus C giving us ABC. So they have the general formula A plus B going into AB, and usually takes place between a metal ion and a non-metal, like iron and sulfide, giving us iron sulfide, just one product. A metal oxide and a non-metal oxide, like calcium oxide. Calcium is a metal, and we have the oxide. So this is a metal oxide, and then carbon dioxide, and the carbon dioxide being a non-metal oxide, giving us calcium oxide. So for example, you've been given an equation to balance, complete and balance, and you have been given calcium oxide plus carbon dioxide. In fact, if you don't know the type of reaction you are dealing with, it will be very difficult for you to even write a product, because let's assume you don't know the type of reaction here. Then you are going to say, which one is going to combine with which? Is it calcium? Or how many products am I going to form? Is it calcium, carbon, oxygen 3, or whatever? It becomes difficult. But if you know that, no, this is a metal oxide, and it is going to, or is combining with a non-metal oxide, then this should be a combination reaction or a direct union. And if it's a direct union, then I'm expecting only one product. And it becomes simple if you know it. If you know that you're going to form one product, then if it is one product, obviously the calcium will be there, the carbon will be there, and the 3 oxygen atoms will be there. So that if you have to proceed to balancing will be easy. And I think in this case, it's even already balanced. There is one calcium, one carbon, 3 oxygen. 3 oxygens is balanced. Combination reaction also occurs between a non-metal and a non-metal, but of a form like this. So we have like carbon and oxygen, giving us carbon dioxide. And that ends our session. There are some here that you can try when you are free. All right, we have some 5 minutes. Let's quickly decide on when to do the remaining 1 hour. And my proposal is Wednesday, 7 to 8. Remember, it's a proposal. If we agree to it, that's fine. Is it okay? Wednesday, 7 to 8.
Yes, sir.
All right. Okay, so if that's the case, please don't fix anything on Wednesday, 7 to 8, because we'll meet and then we'll cover our 1 hour. On weeks that we are able to cover all the 6 in the 2 hours, then it will mean that we'll be free on that Wednesday. Unfortunately, today we may not be able to cover the remaining 2, so we'll cover on Wednesday. Robert, your hand is up.
Sir, please, I wanted to say that it's okay, like the day.
All right. And then also let's get a group. Let's get a WhatsApp group and then get ourselves on it for communication to be easy for us. All right. At this point, if there are concerns, we look at it. If there are no concerns, then I am going to thank you. At least there is some minutes. Those of you that you don't have anything doing and you want to rush to church, at least you can go and receive blessings before they close. There are some churches that at least they spend a lot of time, so you can go for some blessings. All right. And so on that note, I will thank you all for joining, and I'll be hoping to see you on Wednesday, 7 to 8. Thank you, and do enjoy the rest of your day. Bye-bye.
You're welcome, sir. Bye-bye. Robert.
Robert, okay. With the CIA was safety in chemistry. Never back up. Science, society, and
Science,
environment.
technology. Yeah, well, no.